Good afternoon, students. Sorry, I was late a few minutes. So we are going to discuss few problems in tutorial 2. Not so many problems, but they are all quite interesting problems. We start with problem number 1. This you can see as a continuation of the last problem which we discussed in tutorial 1. Right? If you remember, in tutorial 1, the last problem is to calculate the latency of message transfer time. We have considered 3 cases. The first case was that we sent it as a single 5,000 bit packet. Then we divided into small 10,000 bit packets, right? Then we found that the transfer time is reduced. Okay? Then I asked one question, can we reduce it further down to 500 bit packet, 100 bit packet, 50 bit packet, 1 bit packet? So that would not help beyond certain limit. Why? Because we conveniently ignored the header associated with each packet, right? So now we need to strike a balance. The packet should not be too large. It cannot be too small also, okay? And another reason is the retransmission errors, okay? If the packet is very big, even if 1 bit is corrupted, we need to retransmit that big packet, right? So from that perspective, we prefer small packet. But if we send small packet or frames, there will be large number of frames, and each frame will carry header. Okay, so that header need to be transmitted. So that means we are using the link to transmit so many header bits. It's an overhead. Right? So how do we strike a balance, a trade-off? So what is the best size to choose? Okay? Let's look at this problem. This problem answers that question. Suppose a communication protocol involves per packet overhead of 100 bytes of header and framing. Okay, so when we say header and framing, so this includes the framing, let's say count-based framing or let's say flag-based framing and all. So for simplicity, so let's assume that each packet has 2 parts. This is the header and this is payload data. Okay. So we say that this header is an overhead because it does not help. It's not part of data, but from the protocol requirement, we need to attach additional header. There is no way, right? So we call this as header overhead. So this, according to this problem, 100 bytes are used for this purpose. And we need to send 1 million bytes of data. 1 million bytes of data. So obviously, we don't prefer to send as a single packet, because if you send as a single packet, even if 1 bit is corrupted, the entire 1 million bytes need to be retransmitted. So that's not a good idea, right? So it's given that 1 data byte is corrupted, let's say bit or byte is corrupted, and the entire packet containing it is thus lost or damaged, whatever it is, necessitating retransmission of the lost or damaged packet. Though I say lost, it could be damaged as well. So in one extreme end, we do not want large packet because we need to transmit a large packet in the event of errors. On the other side, we do not want to have small packets because small packets means we need to send large number of packets. So each packet should carry header as well, right? Now, the question is this: give the total number of overhead. Here, overhead I refer to the header, the 100 byte headers, plus retransmitted bytes. Because it's given that 1 byte is corrupted, so something needs to be retransmitted for different packet sizes. Packet data size. Data is this one, this part. So let's say packet carries 5,000 byte of data. What is the header overhead? What is the retransmitted bytes? If the size is 20,000, 25,000, okay, what is the header overhead as well as the retransmitted bytes? Retransmitted bytes also a kind of overhead, but due to retransmission, not due to header, okay? Then the next part is find the optimal packet data size. How big should the packet should be? Okay. So let's assume that X be the packet data size. That means each packet carries X bytes of data in addition to the header, and each packet carries 100 bytes of header. Okay. Let n be the number of packets, because the total is 1 million bytes. So depending on the size of each packet, the number of packets will vary. Right? And let O be the header plus retransmitted bytes. Note that 100 bytes of header should be carried as part of each of the n packets. So now, what is the relationship between this n and x? N is the data bytes carried in a packet. Capital N is the number of packets. Okay? Because there are 1 million data bytes, the number of packets n is 1 million divided by x, because x is the data bytes carried by one packet. Okay? And each of these n packets carries 100 bytes of overhead. So the O, capital O, this is the total overhead because of the header as well as retransmission, is n times 100, because there are n packets, each packet carries 100 bytes of header. N times 100 is the header overhead. And 1 byte is corrupted, it's given. So 1 packet is retransmitted. So what is the size of 1 packet, that retransmitted packet? The retransmitted packet carries X data bytes and 100 header bytes. So this is because of retransmission. And this part is because of the total header bytes. So this is capital O. Now we have derived a simple expression. We are ready to answer the first part of the question. Okay, if each packet carries 500 data bytes, what is the total overhead O? That means if X is 5,000, N would be 200, because N is 1 million divided by X. So use X and N here, you get 25,100 bytes. If X is 20,000, that is each packet carries 20,000 bytes, the number of packets will be just 50, because 1 million divided by 20,000 is 50. Now if you use these values of X and N in this equation, you get O as 25,100. Note that in these two cases, the total overhead, that is header plus retransmitted bytes, is the same. Okay, so it so happens that they are same. Okay? But now look at this case. When we carry 25,000 bytes in a single packet, the number of packets n is 40, then O is 29,100. Similarly, you can try with different values of x. You'll get different numbers. So the second part of the question is, determine the optimal packet size. So for what value of x, O is minimum? For what value of x, O, the capital O, is minimum? Okay, so we use very simple theory, it's a maximum minimum theory. I believe you must have studied in a school. It's a very simple theory. It's a very simple differentiation, not a very complex one. So what we do is we express this O in terms of x. O is n times 100 x plus 100, where n is 1 million divided by x. So this O is nothing but this expression in terms of x, because n is 1 million by x. Okay, now we get an expression in x. So to find maximum or minimum, we differentiate it and equate to 0. You get either maximum or minimum. Okay. So dy by dx. So when you differentiate 1 by x, so x is in the denominator. Differentiation of 1 by x is minus 1 by x square. So minus 10 power 8 divided by x square. Differentiation of x is 1. Differentiation of constant is 0. So when you equate to 0, x, what the value of x you get is 10,000. That means if each packet carries 10,000 bytes, in this particular case, that would be the optimum from the perspective of the total overhead, that is header plus retransmitted bytes. Okay? But how do we verify that this is minimum, not maximum? I mean, intuitively you can say it's minimum, but if you want to mathematically verify, then for this value of x, 10,000, you need to check d square is greater than 0. If d square is greater than 0, it's minimum. Otherwise, it is maximum. But let's not worry too much about this theory. Yeah. So when X is 10,000, it is minimum. Any doubt? Students, any doubt? Problem number 2. Small packets are preferred for real-time VoIP, that is voice over IP applications, because that's what nowadays we do, right? We don't use the real landline telephone. So mostly we use internet for speaking, right? Even at home also, when you subscribe to the broadband service, usually they give phone service is free, okay? Because that consumes very, very small bandwidth compared to 1 Gbps or 500 Mbps data rate which you have at home, okay? So this is with respect to that application, but this is also a continuation of problem number 1. With small packet size, a large fraction of bandwidth is consumed by the overhead bytes. So here, the header. This we have already seen. If the packet is small, then we need to generate large number of packets. So to this end, suppose the packet consists of L bytes and 5 bytes of header. So before we look into the question, so let's quickly look at how the voice over applications, they send the packets, how the packets are generated, okay? It's not that, okay, conventional applications like, okay, image transfer or file transfer, email, text transfer, web page and all, you have some kind of files, okay, or message, so that will be fit into different packets and transmitted, right? But real-time applications like voice and video, they are not like that, okay? Let's say voice, so when we speak, right? When we speak, so we generate some signals, right? So amplitude versus time, right? We generate signal, okay, as I said. So our signals, voice signal, usually would be in the range of 3,000 to 3,300, okay? Maybe maximum, let's say 4,000, though they may not be very significant. So if we band limit to 4,000 hertz and transmit it as binary equivalent, okay, then we should be able to reconstruct, okay? At the other side, if it follows sampling theorem, which says you need to sample twice at the rate of maximum frequency and all, some of you might have studied, right? So that's a very useful theorem, okay, to implement this kind of application, right? But we are not going too much into details. So what is done here is, the signal is encoded. The meaning is that we take samples of the signals at a certain rate. Sample rate. So we say samples per second. Let's say we take X samples per second. X samples means we look at this amplitude of the signals, okay, we sample it at different interval. At a certain interval, okay, that's a sampling rate. So per second, how many dots, how many samples you have. And each of these samples is mapped to a binary number. So usually, okay, let's say we use 8-bit binary number. So each of these sample values are mapped to 0 to 255. 0 to 255. So this signal, okay, maybe something like 48, this may be, let's say, 62, this may be, let's say, 85, something like this, right? So we translate the signal amplitude, the actual value, into some value in between 0 to 255. Then we represent this as 1 byte. That is 8-bit. So one sample means you can assume it's 8-bit. So we need to send X samples per second. So obviously, if X is quite large, we don't lose out the values, right? If X is small, let's say you take one sample here, one sample here, one sample here, one sample here, then you lose some voice information, right? The quality will be affected, right? So that's why how many samples we should take, it's twice the maximum frequency component, that should tell. See, for example, if maximum frequency component is 4,000 hertz, so if you take 8,000 samples per second, it's good enough. Even if you take 10,000, 15,000, it will not help, it will not help, okay? So this is how the voice packets or voice data, bytes are generated. That means the analog signal now is converted into bytes, okay, based on X samples per second. So that's the sampling rate. Okay? So now let's look at the question. Consider sending a digitally encoded voice source. This is something like you are encoding the voice signal. Okay? Suppose the source is encoded at the rate of 128 kilobits per second. Of course, you can translate it. Number of samples per second. Okay, one sample means, let's say, 8 bits. So you can easily calculate, okay, in bits per second. So this problem says at the source, the voice data is generated at the rate of 128 kilobits per second, right? And we need to prepare the packet at the source, right? If you look at the switch or router, the packet is received. But at the source, we need to generate the packet. We need to prepare the packet, or we need to build the packet. So assume each packet is filled before the source sends the packet into the network. So first build the required number of bytes, then send it. At the switch and the router, you receive, that is store and forward. Receive all the bytes or all the bits, then send it. But at the source, you need to generate all the required bytes to fill the packet. Okay? The time required to fill a packet is called packetization delay. How much time is needed to build, to prepare a packet, packetization. Okay? In terms of L, determine the packetization delay in milliseconds. Suppose the packet, okay, consists of L bytes and 5 bytes of header. What is the packetization delay? Okay, note that generally packetization delay, we don't consider the header because this refers to the time to fill the data part, payload part of the packet. Okay. So this is quite straightforward. Packetization delay, again, this is something like, it's not transmission time, right? This is the time to collect or prepare the required number of bytes. But that also depends on the rate. So size, again, the formula is same. Size divided by rate, okay, will give you the packetization delay because we are asked to express in milliseconds. And so L bytes means L into 8 bits, 128 kbps. So this translates to millisecond. Okay, K is in the denominator, numerator it is millisecond. Okay, is that okay? Note that this rate is not the data rate or transmission rate. This is it's a representation of the sampling or encoding rate. Okay. Similarly, video also, the real-time video also has, okay, some kind of encoding rate. Okay. Now, question 2b. Packetization delays greater than 20 milliseconds can cause a noticeable and unpleasant echo. This is real time. Okay, it's not that you store the voice file, then you transmit it, video file, transmit it. No, real time it's happening. So packetization delays greater than 20 milliseconds is not desirable. Okay, why? Because that can be noticed at the other side with unpleasant echo. Determine the packetization delay for L equal to 1500 bytes. Let's say you send 1500 byte data or frame. Okay, so this number is derived from Ethernet. So later we see that Ethernet can carry maximum 1500 bytes. Okay, so if you send it as 1500 bytes, what is the packetization delay? Obviously we need more time, right, to fill 1500 bytes, right? So then the other question is, suppose L is 48. That is, if you prepare a small packet, each with 48 bytes, that is the case for ATM. ATM we have not studied, asynchronous transfer mode. Okay, in ATM context we call it as ATM cell. Once it was very popular, okay, but still some networks exist, but no new developments. Okay, so that was promoted, okay, as a good candidate for multimedia applications, voice and video kind of applications. 90s, particularly 90s and early 20s and all, they were very popular, seen as a tough competitor for IP and other things. Of course, we are not studying that in this course, but just remember that ATM packet size is small. Actually, it is fixed, 48 bytes. It's not like IP packet. Every ATM packet size is 48 bytes. Let's answer B first. When L is 1500 bytes, So use this formula, 1500 divided by 16, 93 milliseconds. When L is 48 bytes, the time to fill or prepare the packet is L is 48, okay, by 16, 3 milliseconds. We need only 3 milliseconds to prepare a small 48 byte packet compared to 1500 byte packet. So this is obviously not desirable because it should happen in real time. Right? Of course, we can still implement it, but we need to have at the receiver side mechanisms, adequate buffer, okay, to handle the jitter and other things. So we are not going into the details, but generally it's not desirable. Yeah. Then 2C, calculate the store and forward delay at a single switch for a link rate of R when the rate is 622 Mbps for L equal to 1500 and L equal to 48. Okay, now we see some new terminology, store and forward delay on a switch. So earlier, okay, the switch or router, we were using the terminologies like transmission time, transmission delay, right? This, okay, I take it from another book. So just to introduce some terminologies to you. Store and forward delay at a switch or router is nothing but the transmission time. Because at a switch, we need to transmit on the link. That depends on the link data rate, right? So that means you are given the data rate or bandwidth, you are given the size, you can directly calculate the store and forward delay, okay? Because it goes through the switch, what is the additional time it takes? That's another transmission time. But for the transmission time at the switch or router, we should do both. When you say transmit, we should transmit both header and payload. So when the data size is 1500, including the header 5 bytes, it is 1505. So the transmission time is the size in bits divided by data rate. You get 19 microseconds. So in the case of ATM cells, 48 plus 5, 53 bytes, you get 0.8 microseconds. So if you look at these two, both are in microseconds. So obviously, this is less than 1 microsecond, it's about 20 microseconds. But still, the transmission time, that's acceptable because it's not in milliseconds and other things, right? Because our concern is more on the packetization time, where the difference is much higher. So from that perspective, what we argue is this. Store and forward delay is small for both the cases, 1500 byte Ethernet packet or Ethernet frame. The other side, 53 byte ATM cell. But the packetization delay for L equal to 1500 is too high for real-time voice application. So the packetization delay is the key concern here, not the transmission time. Okay, I think the question itself says small packets are good for real-time voice over IP applications. Any doubt? Okay, problem number 3. What signal to noise ratio is needed to put T1 carrier on 50 kilohertz line? This is the only context we talk about bandwidth, data rate, capacity are together. Okay, so here's capacity and bandwidth. So we know the relationship between the capacity, which is bits per second, and the bit B, this is the bandwidth, the unit is in hertz. This is the true definition of bandwidth. So C equal to B log to the base 2, 1 plus signal to noise ratio. So this signal to noise ratio, as I said, defines or represents the quality of the channel or link. Okay? So if 2 parameter values are given, because 3 values are involved here, 3 variables are involved, right? C, B, signal to noise ratio, right? If 2 are given, you can easily calculate the other one. Okay? So in this case, T1 carrier, the data rate is 1.544. So as I said, these numbers you don't need to memorize. I already given in the table, right? So if numbers are required, I will provide this number as part of the question. If such question is asked in the test or anything, maybe in bracket or something I may give, okay? So this is basically C. Bandwidth 50 kilohertz. Now, so this is the equation. So, okay, C by B, so bring B left side. C by B is 30.88. So C, B. B is 50,000. This is 1.544 multiplied by 10 power 6. So you get C by B 30.88. So that means 30.88 equal to log to the base 2, 1 plus S over N. So what is S over N? 2 raised to the power 30.88 minus 1. Okay? But in signal to noise ratio, you have to express this as 10 log something. Okay? That means you need to find this value, then use this, then you have to find 10 log 10. Okay? Either you can directly, you know the formula to convert the base, use it, or play with your calculator to find the answer. Okay? But approximate value we can easily find, because 2 raised to the power 30 is approximately how much? 2 raised to the power 30 is approximately 10 raised to the power 2 power 20 is how much? 2 power 10 is 10 cube, right? Approximately. That's 1024 actually, okay? So 2 raised to the power 20 is 10 power 6. 2 raised to the power 30 is 10 power 9. So 10 log 10 power 9 is approximately, what is log 10 power 9 to the base 10? Log 10 power 9 is 9, because log 10 power 9 base 10 is 9. So approximately 90. So this will be approximately 90, but if you use, because it's not exactly 10 power 9, so you get 90 plus. Just, you can quickly verify whether the answer is correct or not. Any doubt, students? You have any doubt on this? Problem number 4, I think the remaining problems are short and quite simple as well. Assuming a framing protocol that uses bit stuffing, show the bit sequence transmitted over the link when the frame contains the following bit sequence, excluding flag bits. Suppose we need to transmit this. Okay, the bits, what are the bits transmitted by the sender? That's what it says. And it's given that the sender uses bit stuffing. So bit stuffing means what? After every 5 consecutive ones, a dummy 0 is inserted. That means whenever the sending adapter transmits 1, 1, 1, 1, any 5 consecutive ones, it transmits 1 extra 0. So from that perspective, after transmitting the first 5, 1, there's a 0 inserted. Then next 5, 1, 0 inserted. Note that there are 2 zeros already, so those 2 zeros will be there. It will not be affected. So this 0, which is underlined, okay, or highlighted, is the extra bit, the stuffed bit. Similarly, here also, out 5 ones, there's a 0. So, and here also, there are 5 consecutive ones, so there is a 0 inserted, right? So what the receiver will do, the receiver will receive all the bits. So whenever the receiver receives a 0 after 5 ones, so the receiver knows that this 0 is a stuffed bit that will be ignored or dropped. Is that fine? Yes? Problem number 5. Assuming a framing protocol that uses byte stuffing, show the original data bytes extracted by the receiver upon receiving the following byte sequence, excluding flag bytes. The flag bytes are not shown here. Okay? What is the fraction of bandwidth wasted due to stuffing? So the receiving adapter receives this, but it's a byte-oriented protocol. So byte-oriented protocol, the convention, okay, or the standard is that if the sender wants to transmit, let's say 7E, it will transmit 7D followed by 5E. If the sender wants to transmit 7D, it will transmit 7D followed by 5D. So when the receiver receives 2B, it access 2B. It's hex notation, okay? So it's actually it is receiving bits which represent 2B. Then it receives 7D. When it receives 7D, it looks into the next byte. The next byte is 5D. So this 7D, 5D is replaced by 7D. Now, receiving adapter receives another 7D, so the next byte is 5D. So these two will be replaced by 7D. That means 5D is dropped. That's what it means. Then it receives 5D. 5D will be 5D. So note that, okay, when 7D precedes 5D, it has a different meaning. But here it's just 5D. 5D means 5D. 5E, 5E. Now the receiver receives 7D followed by 5E. So because the second byte is 5E, this will be replaced by just 7E. 0E, 0E, 7D followed by 5E. So these two will be replaced by 7E. Okay? But note that before that, the sender will send 7E as a flag, and at the end, this also will send 7E as ending flag. So this is not shown here because it's also clearly given excluding the flag bytes. Okay? Now, the next question is, what is the fraction of bandwidth wasted because of stuffing? So note that the sender has transmitted 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 bytes. Out of 12 bytes, okay, only 1, 2, 3, 4, 5, 6, 7, 8. 8 are useful. 8 are useful. The 4 bytes are stuffed bytes, extra bytes. So 4 out of 12 bytes, okay, they also use up bandwidth. So that we say is a fraction of bandwidth wasted, 1 over 3. That is about 33.33%. Is that clear? Yes? Problem number 6. A receiver receives a bit stream, including the CRC bits. So there's a difference between sender and receiver, okay? Suppose the divisor polynomial used is x square plus 1. X square plus 1 is 101, okay? Explain if the receiver can detect any error. So the receiver has to carry out CRC test. So what it can, so sender side, note that sender side we have only message bits, okay? So it has to add few zeros first, k zeros, right? So here what's the value of k? There are 3 bits. Okay, so this is x square, so k equal to 2. K equal to 2, right? So sender side, you have message bits, it adds 2 zeros, then carry out the division, then subtract the remainder, you get the entire sequence including the message bits followed by CRC bits. But the receiver, what it does is, it divides all the bits including the CRC bits by the divisor, and it checks if the remainder is 0 or not. If the remainder is 0, it will declare that there is no error, but may be correct or may not be correct, okay? But if you get non-zero remainder, 100% sure there is an error. There is an error. So in this case, when you carry out division, you get remainder 0, 1. So the receiver can detect error. Anyway, I also carried out this. Difficult to put it into this, so I put it on the paper and scan it. So this is the given data stream 111011010, including the CRC bits. Don't try to add zeros and other things on the receiver side, okay? 101, so you have to use, just remember, if the divisor has 3 bits, you have to use 3 bits, and the most significant bit should be 1. Don't try to convert the binary number into equivalent decimal. Don't convert this 111 as 7 and this is 5. No, don't try to do it, okay? Because this has an equivalence polynomial theory. So you should just follow the modulo 2 arithmetic and the division procedure. 1, 101, 1 minus 1, 0, 1 minus 0, 1. So because we have only 2 bits, you have to bring one more bit down, 0. So 1, 101. Note that 100 is 4, 101 is 5. Don't think that you cannot subtract 5 from 4, okay? So I'm repeatedly saying. So you should think in terms of the polynomial, something like x power 5 or something, okay? So 0 minus 1, 1, 0 minus 0, 0, 1 minus 1, 0. So actually here we have only one bit. It should start with a non-zero, right? So you bring one bit down, you have 2 bits, not adequate. So put 0 in the coefficient. One more bit down, 1, 1, 0. So 1, 1, 0, 1, 1, 0, 1, 0 minus 1, 1, 1 minus 0, 0. Bring this 1 down, 1, 1, 1. So 1, 1, 0, 1, 1 minus 1, 0, 1 minus 0, 1. So bring the last bit down. So you get 0, 1. So it's a non-zero. So it's not 0. So error can be detected. Is that okay? Note that we are not interested in the coefficient. Sometimes students don't put the 0, okay? To some extent it's okay, but we are not interested in the coefficient. We are interested only in the remainder. The last problem, using the properties of CRC, verify if the generator polynomial is another terminology. The divisor polynomial is also called generator polynomial. We call it as divisor because it's used to divide. We call it as generator because it's used to generate the CRC. So you can look at different perspective, okay? So from that perspective, we call it generator polynomial. 1, 0, 0, 1. Now the question is whether it can detect any single bit errors, whether it can detect any odd number of bit errors. Let's say 105 bits are corrupted. That means odd number of bits are corrupted, right? Can you detect it? So it follows the theorems of facts which we listed in the last slide in the in lecture notes 3, right? Last slide in the lecture notes 3. So it can detect a given divisor polynomial can detect any single bit error if both x power 0, x power k terms are present. Right? So that means this should be 1, this should be 1. That's what it says. So it can detect single bit errors. And to check whether it can detect odd number of bit errors, we need to check whether it has a factor x plus 1. Okay? So you need to check whether this polynomial has factor x plus 1. So how do you find factor? It has a factor. So you need to divide and see whether you get 0 or not, right? It's a factor. So when you divide it, don't divide it in the polynomial. Okay, try to divide it in binary. Okay, because we use modulo 2 arithmetic. Polynomial here is x power something plus. It's not plus or minus. It can be plus or minus. Okay, so sometimes you don't get it if you do it in the polynomial. But you need to properly use plus and minus, then you will get it, right? So better you carry out division in binary. So how do you represent 1, 1 as in binary? Sorry, x plus 1, binary is 1, 1, right? So you can carry out the division and you can verify yourself. I leave it to you. So we are done. If you have any doubt, so I can stay here for some more time. If you have any doubts, I'll be happy to clarify your doubts on this tutorial or previous tutorial or any other lecture notes. Okay? So other students who do not have doubts, so can leave. So we'll meet again on Monday. We have 2 more weeks to go. Any doubt? Yes? No, that's why I said don't try to convert into binary. 1, 0, 0 is 4. That's your question, right? So this is 4, this is 5, correct? So don't convert it into binary. Because equivalently in polynomial, this is something like x power 5 something, x power 5 something, right? So that's why I said don't convert into decimal value. What is important is this should be 1, this should be 1, and as long as they both have the same number of bits, 3 bits and 3 bits, you can subtract. Correct? You should have same number of bits, and the first bit should be 1, here 1 and here 1. That's all. Don't try to convert this into decimal value because we are not carrying out any decimal division or anything. Yeah. Is that clear? Yes? Okay. Yes. Yes. Yes, a proof. You are interested in knowing the proof? You want to know the proof? Maybe I can share it with you later. That's proof by contradiction, okay? That proof, this is something like, okay, puzzles or riddles we do, right? So there's some object is stolen. How do you find the thief, right? So you assume this fellow is a thief. Then it will lead to some contradicting statement. Then we say, okay, this fellow cannot be a thief, right? So there's a proof by contradiction. Are you familiar with those proof techniques, formal proof techniques? Okay. Maybe if you drop me an email, I can. In the past, I used to teach. I can decode and I can send it. Okay. But it needs some time to discuss here. Yes. You had doubt? Okay. Here? Here. Seven E, after 7E? Here. Okay, 7E, then 5E. The first byte is 5E, is it? So, no, because whenever the receiver receives 7E, correct? It knows that 7E is the flag. It's not part of. So this will be taken as the flag. So then when it receives 5E, that is 5E. Yeah. Is that okay? Yeah.